In today's programme, we'll hear from a chemist from the British Antarctic Survey who's returned from that far-off place to tell us that not every bit of global warming is our fault, or mine. You'll also hear how the BAS scientists can tell how the world has changed over thousands of years.
You're listening to The Science Show on Cambridge 105.
In this section called Scientists at Work, we talk to people who, for some reason or another, find themselves working, researching or thinking about science in Cambridge, England. Human activity has contributed to global warming and melting of ice shelves in the Antarctic. It's complicated because it seems that the climate also changes on its own agenda too. So I spoke with Dr. Robert Mulvaney at the British Antarctic Survey. He's based on the west edge of Cambridge. He's nicknamed the Iceman in one story.
Excellent. By the way, I'm going to pause the interview after about 10 minutes to ask you something, Roger, but for now, hit play.
So we're here at BAS, Dr. Robert Mulvaney. Robert, what does the British Antarctic Survey do?
Okay, the British Antarctic Survey is about 450 people, of which about 180 are scientists, all sorts of scientific disciplines. We work in Antarctica, where we have several bases, 2 ships, 5 aircraft, and we do a whole range of science in the Antarctic region. So that could be biology and marine sciences in the surrounding oceans, it could be geological research in the interior, or it could be, in my case, glaciology. That's either looking at the ice to see how the mass balance is changing, so whether or not the ice is, the continent is getting thicker or thinner in response to climate change. And in my case, I drill into the ice to measure what's happening in the atmosphere and what's happening to the climate over periods of several 100,000 years.
You drill. So how did you get into this? Did you work on roads somewhere?
Now, a long, long time ago, when I was a teenager, someone gave me a book called Great True Adventures in Ice and Snow. These were extracts from diaries of people like Scott and Shackleton and people like Cook and Peary in the Arctic. And I was just fascinated by these people that went to the polar regions, and they became heroes of mine. To be honest, at that time, I have no idea that people still worked in Antarctica. I thought that was something that exploration 100 years ago, and that was the end of it. But as I got older, I realised that people work in Antarctica, and in Greenland, of course. And it became an ambition of mine to work in the polar regions. And although I went to university as a chemist with the intention of being a forensic chemist in the end, so I learnt analytical chemistry at university, there came an opportunity when I was in my early 20s to go to Antarctica to do analytical science on ice. And I jumped in to the opportunity, went to the Antarctic, and I've been doing it ever since. So I've now been to the Antarctic 17 times, Greenland 3 times. So I've worked in both polar regions, still measuring, still doing analytical chemistry on ice.
Can you tell us what your most recent project's been about?
So this year, in February, I've completed a new drilling at a place called Fletcher Promontory, close to the highest mountain in Antarctica, called Mount Vinson. We drilled all the way through to the bedrock, 654 metres deep, so I hit the bottom of the ice sheet, 654 metres down. Very hard work, team of 7 of us, working 24 hours a day in shifts on the drilling rig to get to the bottom. And what we'll do is we'll bring back a cylinder of ice right from the surface all the way to the bottom. It's a cylinder about 10 centimetres in diameter. Okay. We chop it up into 80 centimetre pieces in the field. We pop it into insulated boxes, and then they come back in a reefer container on the ship all the way back to the lab here. Once they're back at the lab here, they then get cut into small pieces that would go into a range of analytical instruments that allow us to tell you what's happening to the climate, what's happening to all the material in the atmosphere, things like pollution. Modern pollution is in there, but also tells us what's happening in the atmosphere itself in terms of things like carbon dioxide and methane, so we can look at the greenhouse gases. Now, why I drilled this core in particular, I wanted a record that went back to what we call the last interglacial, so the time 120,000 years ago, when the climate was just as warm as today, perhaps even a little bit warmer. We think the sea level was even 6 metres higher than today. And I wanted to look at that particular area of Antarctica and say whether or not the ice was still present. There's a hypothesis that the ice from that region of Antarctica may have actually disappeared in the last interglacial, or at least substantially reduced in amount, and that might be where the 6 metres of sea level rise came from this disappearing part of what we call the West Antarctic ice sheet. So I've drilled a core all the way back to the bottom. I know there's going to be 120,000 year old ice at the bottom because we understand the age-depth relationship. So I want to see how much ice was still left in Antarctica and what the climate was like at the time.
If I take out a piece of this ice cube, which goes a long way down, you'll put it in your lab and you'll put it in a test tube. What do you do with it?
What we do is we get it back to the lab here and we cut it into all sorts of sections. So some sections will go off to measure the gases, so that's where we get things like carbon dioxide and methane. Now these are little tiny air bubbles locked up inside the ice. So ice has got air in it, about 10% of its volume is air.
Yeah, right.
And we can take out that air, and it's been locked up since 100,000 years ago. So we can just tell you what was in the atmosphere 100,000 years ago. It's fairly easy to do. We also measure what we call the isotopes of the water molecules. So water is H2O,
Yep.
and there are heavy and light isotopes of oxygen, heavy and light isotopes of hydrogen,
Yep.
and we measure the ratio of the heavy and light isotope. So if I have an instrument which I can measure the ratio of the hydrogen atoms, so hydrogen and deuterium, it turns out that in a warm period you get a little bit more of the heavy isotope. Now the origin of the water, of course, is the ocean surrounding Antarctica, and when you've got a warm climate you get a little bit more of the heavy isotope evaporate from the ocean. So we see a little bit more of the heavy isotope in the ice. So what we do is by measuring the ratio of the two isotopes we're able to tell you how the climate has been changing.
How do we know that what you're measuring is not an artefact? I mean, how do you know that you're getting good information?
If we look at, say, for the isotopes of water, which tell us about temperature, what we're able to do is go to different regions of Antarctica where you have a different seasonal climate. So we can take the average temperature at a particular site, and then we can take an average of, say, the top 10 metres of ice and look what the average isotope signal is. And then when we plot the average isotope signal against the average temperature signal over the whole of Antarctica, we get a nice linear graph, which gives us, if you like, a calibration between temperature and isotopes.
Good.
If you look at things like the gases that are trapped in the ice, so these are the gases that are trapped in bubbles deep in the ice, what we need to understand is whether or not they could have been modified in the ice after they've been locked up. So what we're able to do is take the top 80 metres, where the ice is still porous and there's gases percolating through it, and look at how the modern changing gas concentration in the atmosphere. Carbon dioxide is changing about 2 parts per million each year, so we can see a changing atmosphere at the moment, and we look at how that is being recorded in the ice, and we can see that what we're seeing in the ice represents a real signal. So if, for example, you look at carbon dioxide measured in the atmosphere at places like Mauna Loa, they began in March 1958, and ever since then carbon dioxide has risen to about 2 parts per million per year. Our ice core records now overlap that by about 20 years, and we can see that we're measuring the ice cores exactly the same levels as we see in Mauna Loa. So again, it's a way of looking at, this time it is a control. We can see real atmosphere measurements, and we can see we get exactly the same measurement in the ice.
Before we go into the cold room, which I'm scared of now, tell us about your most recent survey, because that has produced some very interesting and very useful information to us.
3 years ago, we went to a place called James Ross Island. James Ross Island is right at the north of the peninsula, and it's situated in a place where the climate is warming very rapidly. So over the last 50 years or so, meteorologists have measured a warming of about 2.5 degrees Celsius. So it makes it one of the fastest warming areas on Earth. And as a consequence of that warming, the ice shelves, now this is the floating ice that's several hundred metres thick, that's flowed off the main Antarctic ice sheet and is floating on the ocean. It's not sea ice, that's not ice that seasonally freezes on the surface of the water. This is ice that's flowed off the land and is now floating on the ocean. We've seen some of these ice shelves that we thought had been present since the last glacial period have broken up and disappeared.
Okay.
So what we wanted to do is go to this area and try to give you a climate record that went a bit further back than the 50 years that the meteorologists have got. And in fact, we got a climate record that goes all the way back into the glacial period, so it goes back at least 15,000 and probably as much as 45,000 years. And what we can see is that warming from the Ice Age into the present warm period. And then what we found is that in the early part of what we call the Holocene, the last 10,000 years, the climate was about the same temperature as today. It then cooled a little bit, and then about 2,500 years cooled some more. And then the warming that we're seeing at the moment began about 600 years ago. But it began very, very slowly. And in the last 100 years picked up speed. So at the beginning of the warming 600 years ago, it was about 0.2 Celsius per 100 years. And we're now at about 1.5 degrees Celsius per 100 years. So the rate of warming has increased quite rapidly. And the rate of warming we're seeing in the ice core record matches the rate of warming that meteorologists are seeing. So we're seeing the same signal. But what we're now able to say is actually probably began as a natural warming 600 years ago. A slow natural warming from, if you like, an unusually cold period in the Holocene. But what we're seeing now, in the last 100 years or more, is a much more rapid warming, which we think is a consequence of human-induced climate change on top of a naturally changing climate.
A quick read of your website. I noticed that you're not saying, way hey, it's all right now.
We're not saying, way hey, it's all right now. If you look at our record, you could say that 10,000 years ago, the climate was the same temperature as today. So what's the problem? Of course, we're not living in the climate 10,000 years ago. We're living in a modern climate, the modern climate for the last few hundred years. And what we're seeing is that modern climate is changing really rather rapidly at the moment. It began perhaps 600 years ago as a natural warming, but what we're seeing now on top of that appears to be a much more rapid warming that could be human-induced, either as a consequence to the changing greenhouse gases, or in fact even as a consequence to the change of the Antarctic climate in response to the ozone hole. The ozone hole itself has changed the climate in Antarctica. So what we're seeing is in the last 100 years is the stacking together of something like carbon dioxide-induced climate change plus ozone hole-induced climate change on top of a natural warming.
Before we go and have a look at these ice cores that you measure, if you were to help me have two graphs in my head, one graph shows the global warming due to climate change, and another graph shows the global warming due to me using my central heating and car and such like.
I have two graphs in my mind. One is if we look at the climate change over the last 800,000 years, we can see we've been in and out of a glacial period 8 times. And then if we then overlay the carbon dioxide in the atmosphere on the top, we can see that the carbon dioxide and the climate are very, very highly synchronised. In a cold period, we'd expect to see something like 190 parts per million carbon dioxide. In a warm period, we'd expect to see somewhere around about 280 parts per million of carbon dioxide. But today we're somewhere near 390 parts per million of carbon dioxide. So if you like, the difference between an ice age and a warm period is about 100 parts per million change in the atmosphere. Now this is carbon dioxide that's coming from things like deep ocean sediment, so it is natural carbon dioxide being released into the atmosphere, partly as a response to the climate changing, which is partly in response to the Earth's orbit around the Sun and the change in the amount of insolation or sunlight the Earth receives from the Sun. In the last 2 centuries, we've seen another 100 parts per million increase in the carbon dioxide, which has to have come from things like burning fossil fuels. Now, the reason why we think that is if we look at the last 1,000 years of carbon dioxide in the ice cores, then for most of the last 1,000 years the level is 270 parts per million, exactly the same level as we see in the previous interglacial 120,000 years ago. Then round about the late 18th century, the carbon dioxide starts to increase. In fact, it starts to increase around about 1770. That's around about the invention of the steam engine. So as soon as the steam engine was invented, we start burning fossil fuels, the carbon dioxide in the atmosphere begins to increase. So we can see this increase beginning, and it's very rapid, more and more rapid as we get towards the present. And we can see, if we look at the climate over the last 100 years, you can see that through the 18th century, largely stationary through the 19th, and then through the 20th century, this rapid and gradual increase all the way to the present.
Okay, thank you very much, Robert. Let's go and have a look at your ice cube collection.
Okay, we're pausing for a moment there because I can tell, Roger, you had an epiphany.
Okay, well, it's not quite as big a word as that, but it struck me that as each year passes, Antarctica has gained another layer of ice, and each year it traps the air in the atmosphere and it freezes it. And this has been going on for thousands of years, just waiting for us to develop the instruments that can measure it. A fact that's now become clear to me is the fact that Antarctica is a time machine, and that's why they bother to spend so much money up there. So just like in archaeology, you drill down to find out what the world was like years ago. In Antarctica, drilling down 3,000 metres, 3 kilometres, and they get a record of the Earth going back maybe 800,000 years.
Right, and very exciting work. But I was wondering, with all the people around the Antarctic nowadays, how might all this activity add contamination or noise that affects their findings? What do you think, Roger?
That's a seriously good point, Chris, actually, because in a second you'll hear Robert talking about measuring things in parts per billion. But to answer your point, the BAS people totally clean up after themselves. So, for example, they don't leach waste into the ice, and they bring the whole lot back.
I hope that means that they're separating their beer bottles from their used beer bottles, if you know what I mean.
I didn't ask, but at this point we go into the cold lab.
Don't you mean the Bass time machine?
Yes, the time machine. Here we go. Oh my, it's cold in here. Where are we, Robert?
Okay, we're now in the what we call the cold laboratory. It's a freezer. It's minus 25 in here, and it's where we actually process the ice. So we don't store ice here. Most of it's stored off-site in a big commercial freezer. I've got hundreds of boxes like this. This is an ice core box. This is how we bring it back from Antarctica.
Yep.
So hundreds of boxes like this in a big commercial freezer, and we just bring on site what we're actually working on. So in here, I'm either cutting the core up on the bandsaw over here, or I'm melting it on this what we call a melt head here. You see this gold-plated melt head?
Okay.
Stick a column of ice on that. Here's one of the columns of ice. And as it melts, it continuously runs into a whole range of instruments out there. There's a mass spectrometer out there, an ion chromatograph, there's various spectroscopic techniques, there's an instrument for measuring carbon dioxide and methane, there's an instrument out there for measuring things like the isotopes of the water molecules. So as we continuously melt this ice, it goes into this range of instruments, and we almost instantly get our signal. And where we've got something like this is a relatively shallow core. We'll probably have several seasonal cycles in this, so we'll be able to see the seasonal cycle in a lot of the chemistry.
When you say see, you mean...
What I mean...
I look at this and it just looks like stuff I put in a gin.
Yeah, so when the data comes out of the instruments, what we can see is a clear pattern between the summer and the winter signal. So, for example, we see a clear seasonal cycle in the isotopes of the water molecules because they represent temperature. But we can see things like non-sea salt sulfate. That's what we call the sulfate that's coming from the atmosphere. And it's coming from marine organisms. They give off a gas called dimethyl sulfoxide. It's oxidised in the sunlight, so in the Antarctic summer, and then we see sulfuric acid in the ice. Very tiny amounts of it, only tens of parts per billion, but the sulfuric acids come from the gases being breathed out by the marine organisms. Every so often we'll see a big spike in sulfuric acid, which has come from a volcano. So, for us, things like the Tambora eruption in 1815 is a very big spike of sulfuric acid in our ice. Well, I say very big, a few hundred parts per billion. And it's like a dating mark for us. We know it's there, we know it's in 1815, so when we see this spike, it's a way of saying, oh, that year must be 1815.
Goodness, that's big. So over there, bandsaw.
There's a bandsaw. Here's a small ice. Here's a section of ice. So this is a section that's come from 48 metres down on the Dyer Plateau. In fact, it was drilled in 1990. It's only just come back out of the store. This is still porous, so at this point the air is still circulating around the grains of the ice. When you get down to about 80 or 90 metres, all that porosity will disappear and the ice will become locked as discrete bubbles. And I'll just pick up a piece of ice here so you can see it. So we're down probably below what we call the pore close off now. I'll just rub that so you can see it. Can you see the air bubbles in that?
Yes, definitely.
Okay, what I'll try and do for you, because it's just I'll grab a piece of ice and I'm going to drop it into some hot water. And with a bit of luck, you'll be able to hear the bubbles as the ice melt.
Okay, what we have here is a 500-year-old piece of ice and a beaker of hot water.
You can see all the air coming off it.
And I can see bubbles of air.
So that's all the air being released. This is old air. So if I measured the carbon dioxide in that, this is about 500 years old, I'd expect to see something like 270 parts per million in that air. Whereas if we measured the atmosphere today in here, we're probably somewhere near 390 parts per million, about 120 parts per million higher than is being evolved from this. I'm just going to pull this one out of the shelf here.
Okay.
This is quite a bit deeper now. This is from a place called Berkner Island. It's a deep ice core, bag number 1235. It's about 650 metres down in the ice sheet, and this ice is about 27,000 years old. So when this ice was laid in Antarctica 27,000 years ago, it's been remained frozen ever since then. The great northern hemisphere ice sheets came all the way as far south almost as Cambridge, so where we're standing today would have been under the ice sheet from the northern hemisphere ice sheets.
Interesting.
See the air bubbles in that?
I can.
Smaller. We're deeper in the ice, so the air bubbles are getting smaller just by the compaction. If I measured the air in this and measured the carbon dioxide in this one, I'd expect to see something around about 190 parts per million. So 190 in this, 270 in that, and in the atmosphere today 390.
So this collection here, which looks like the rolls of fabrics in John Lewis, should we
Yes,
say?
it is. Yeah, these are the things that we're actually working on at the moment. There's a range of cores in here, so some of them will be old, so they're about the 27,000-year-old ice there. Some of them are fairly new. This one is probably about 1,000 years old. This is from a place called Dyer Plateau that we're working on. These are some shallow cores. These really are shallow, so these are only 7 metres deep there. This is from a place called Dronny Moorland. What we're interested in is the climate from different regions of Antarctica. So we're looking at the climate and the atmosphere and things like the material that's coming from the oceans. We're looking at dust from the continents. We're measuring all these things in the ice, and we're seeing how the local and regional climate for Antarctica is changing. So we're not only interested in the global climate and the global atmosphere, but we're looking at the regional responses as well to the climate change.
Well, thank you very much, Robert. I can see this whole area is huge, and you've got a lifetime, and you've already spent a lifetime trying to find out things.
I think that's right. I mean, I've just picked out a core there that we're starting to measure now that we collected in 1990, and I'm still collecting cores today. These people will be measuring these cores that we're collecting today long beyond the time that I'm still working
Well, I
on
hope
them.
you live long enough to finish it. Can I just say, it's just really cold.
Many thanks to Dr. Robert Mulvaney of the British Antarctic Survey. We'll put a link to their website on our site so you get all the research details.
That's pretty much all for today's show. Scientists at Work is made by the Science Show team on Community Radio Cambridge 105. You can also find past episodes on the website www.cambridge105.fm. You can also subscribe to future podcasts with the iTunes Store. You can get in touch with us on the email science@cambridge105.fm or on Twitter @105science. Till next time, it's bye from the Science Show team of Roger Frost and Chris Crease.
You're listening to The Science Show on Cambridge 105.